All right, let's dive right into this explainer and demystify how diffusion models actually edit existing images. We hear so much about text to image AI just conjuring up brand new things completely out of thin air, right? Well, today we're looking right past all that basic generation. We're going to explore the incredibly complex machinery behind fixing and altering the images we already have. And you know what's really fascinating? The massive business reality behind all this. A whopping 70% of billable image work in production isn't even about making new things. It's about fixing and editing old ones. We're talking about swapping out a background, removing some completely distracting logo, extending a canvas, or maybe regenerating a weird-looking AI hand. Inpainting, which is basically the art of AI editing, is where diffusion models truly earn their keep in the real world. So, here is our roadmap for today. We'll start with the AI editing problem, explore how proper inpainting works, unpack the developer's editing toolkit, go over avoiding common pitfalls, and finish up by looking at shipping for production. Part 1. The AI editing problem. Let's start with the absolute fundamental problem of modifying a specific part of an existing image while keeping the surrounding pixels absolutely identical. Picture this. A client sends you a flawless product photo, but there's an incredibly ugly sign right in the background. You can't just run standard text-to-image from scratch, or you're going to lose the product entirely. You'll end up with a different color, different lighting, a totally different product angle. What you need is targeted regeneration. And this really boils down to two main concepts. First, we have inpainting, which is essentially filling the hole by regenerating inside a mask while perfectly preserving the outside. Then we have outpainting, which extends the canvas beyond the original borders while keeping the inside completely intact. Every major diffusion pipeline today ships with these modes, but the big question is, how do they actually pull it off? Moving right along to part 2, how proper inpainting works. Well, let's look at how not to do it first. The naive approach is basically just slapping a mask on a standard text-to-image generation. At each sampling step, you try to replace the unmasked region of the noisy image with the clean image. And spoiler alert, this works incredibly poorly. Why? Because boundary artifacts just bleed everywhere. The model has absolutely no information about what is supposed to be inside that masked region, so the edges clash horribly. It's a mess. So the crucial takeaway here is that you have to use a proper inpainting model architecture, specifically a modified 9-channel UNet. Instead of the standard 4 input channels, this absolute powerhouse takes 9. It takes the noisy latent image, a compressed VAE encoded copy of your source image, and a single-channel mask. Because of this setup, at inference time, the model can actually see the surrounding unmasked region as a clean conditioning signal. It knows exactly what's around the hole, so it can produce a beautifully coherent completion right inside it. If we were going to build a toy version of this from scratch, we'd follow 4 basic conceptual steps. We'd start with our standard multi-dimensional diffusion data, train our denoiser over all those dimensions, and then, at inference time, we'd run a mask-aware reverse process. And honestly, the beautiful thing about step 4? Outpainting is literally just inpainting, but with the mask inverted. You just mask the new, non-existent canvas and fill the rest with the original. Fundamentally, it uses the exact same training objective. All right, let's jump into part 3, the developer's editing toolkit. Think of this as your ultimate developer cheat sheet for real-world applications. When engineers need to match algorithms to highly demanding client requests, they have to pull out very specific pipelines. Need to remove a small object? You grab SDEdit or Flux-Fill. Want to replace a background entirely? You generate a mask with Meta's Segment Anything model, or SAM, and feed that right into SDEpaint. And hey, if you need to regenerate a mangled AI hand, you don't just use inpainting. You combine it with ControlNet OpenPose to actually force the model to respect human anatomy. It is all about picking the right tool for the job. Now, when it comes to whole image editing, there is a pretty stark difference between approaches like SDEdit and Instruct Pix-to-Pix. SDEdit is amazing because it requires absolutely no retraining. You just add noise to your source image up to a certain time step t, and then denoise it with a brand new prompt. It essentially trades perfect fidelity for creative freedom. But you'd pull out Instruct Pix-to-Pix when you want to explicitly command the AI. Because it's fine-tuned on image and instruction triples, you can just type a natural command like make it sunset or add a dragon, and the model intelligently edits the scene for you. Going back to SDEdit for just a second, controlling your noise level is absolutely everything. I mean, your starting noise level literally dictates your final output.
If you start at a time step of 0.3, the output remains nearly identical to the source, which is perfect for tiny little stylistic tweaks. Bump that up to 0.6 and you get moderate edits that preserve the basic structure. But if you push that noise level all the way up to 0.9, you are practically destroying the original source and generating a whole new image from near noise.
But what if you're stuck? What if you don't actually have a specially trained 9-channel inpainting model available to you? Well, Repaint is your clever fallback. It's a totally training-free technique that uses a standard model. During the reverse denoising steps, it periodically resamples, so it literally jumps back to a noisier state occasionally to force the image to blend better, which significantly reduces those ugly edge seams. Which brings us to part 4, avoiding common pitfalls. Because honestly, as clever as these tools are, the process is an absolute minefield. There are technical dangers everywhere that will immediately ruin your output. If you're getting visible seams, it's usually because gradient info isn't flowing, so you need to dilate your mask by 8 to 16 pixels to fix it. Getting a weird, hyper-saturated patch of color, that is CFG interaction. Your classifier-free guidance is just set way too high for a small masked area. And you definitely have to watch out for the SDEdit fidelity cliff. If you push your noise past 0.5, your main subject's identity might completely vanish in the blink of an eye. But out of all these pitfalls, prompt mismatch is definitely the most common trap for beginners. You absolutely must describe the entire final scene to the model, not just the newly edited piece. If you mask a chair because you want to add a cat, and your prompt is literally just a cat, the model might generate a cat floating in a void, completely ignoring the room around it. You have to tell it the whole story. Say, a cat sitting on a chair. And finally, part 5, shipping for production. So we've got the theory down, we know the tools, but what are the harsh, boots-on-the-ground realities of actually deploying these pipelines to live users? Well, 5 seconds. Just take a moment to let that sink in. 5 seconds is the maximum round-trip time users expect when they tap Edit on a web app or on their phone. If they're waiting 10 or 15 seconds just to remove a background object, they are closing your app, no question. And that makes this entire architectural process extremely latency sensitive. Hitting that ruthless 5-second mark means you are basically going to war with bottlenecks at every single stage. In production framing, you're often totally bound by time to first token, meaning how fast you can actually get the generation started. Look at the crazy adjustments developers have to make. The high-quality SAM HMask generator takes a sluggish 200 milliseconds, so you have to swap it for SAM VIT-B to get that down to 40 milliseconds with barely any quality loss. Also, if a user is doing iterative edits in a UI, please don't waste half a second re-encoding the image through the VAE every single time. You just pass the previous latents directly and skip that step entirely. Every single millisecond counts here. Which brings us right to the bleeding edge, 1.5 seconds. That is the blazing fast edit speed achievable on a massive H100 GPU using Flux context. And this represents the 2025 answer to all of these latency bottlenecks we just talked about. Instead of having a separate mask generation stage and a separate VAE encode and a separate noise sweep, models like Flux Context process the source image and the instruction together in a single, incredibly fast forward pass. So that leaves us with a fascinating and maybe slightly terrifying question to wrap up this explainer. As architectural advances rapidly collapse these complex, multi-step pipelines into a single, lightning-fast 1.5-second pass, what does the future of manual image editing actually look like? Are we witnessing the end of pixel pushing and masking by hand as we know it? It's a pretty profound shift in how we create and fix our digital world. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.